Section 4.4 is called the fundamental theorem of calculus. Anytime you see fundamental theorem in mathematics, it means it's really important. There's fundamental theorems throughout different courses of mathematics. Whether it was presented to you with that language or not, you've seen some of them. One of them is the fundamental theorem of algebra, and it talks about how you can factor things. It usually shows up, it shows up in our college algebra course, but it would be in an Algebra 2 or even maybe the end of an Algebra 1 course in high school as well. Again, it may not have been presented to you that way. But it's really crucial, it's really important for what continues. And what this is actually going to do for us is connect some of the things that we've been doing in the last three sections all into one. So in particular in section 4.3, one of the things that we looked at is this notation called definite integral, where we had a lower limit of an upper limit of integration. And there's only two things that we actually were able to do in that section. One was a geometric formulas of things we've seen before. For example, maybe it was the shape of a triangle, and you can find the area of a triangle really easily, right? But in general, we want to be able to do it for any general form. It doesn't need to be a triangle. We want it to do something that's very specific. And so that's actually the connection point for the fundamental theorem of calculus. So if f is continuous on AB and capital F is any antiderivative f, then the definite integral from a to b of f of x dx is the antiderivative, capital F of x, evaluated at b, minus that antiderivative evaluated at a. Okay, so we're going to do an example. We're going to do a lot of examples of this. And we're going to do one here that's actually one that we could evaluate this and do this. In fact, this might be the exact same one we did last time. It's not, because the limits of integration aren't at least the same. But this is a line. If I were to do negative 3x plus 4 and I were to graph it, I would end up with a shape that's either a triangle or a trapezoid, something like that. I would be able to do this with a geometric formula. That's not what we're asked to do here, but it is something that we could do it another way and verify that we've done it correctly. What this is asking us to do is to use the definite integral. So we're going to take an antiderivative, just like you did on your gateway and everything else, of negative 3x plus 4. So what is the antiderivative of negative 3x? Thank you. Negative 3x squared over 2, right. And then what are we going to do with that 4? 4x. Yeah, plus 4x on the end. Okay, so here's, and technically we would put a plus c. I'm going to show you real quick that we're not going to need plus c's on this, but for this one example, I'm going to show you why we don't need them. So after we take our antiderivative, we're going to put kind of a vertical bar on the end, and we're going to put that 5 on the top, and we're going to put the 2 on the bottom. And we're going to show that we're going to plug in the number 5. So I have negative 3 times 5 squared over 2 plus 4 times 5 plus c. And all of that is going to subtract off. And now we're going to plug the 2 in. So negative 3 times 2 squared over 2 plus 4 times 2 plus c. That's the antiderivative, or the fundamental theorem of calculus that we just saw. It says take the antiderivative, which we did, and then plug in the upper limit of integration, which we did, and plug in the lower limit of integration, which we did, and we're going to subtract the both of them. Now, I want to see real quick with you, do you see what's going to happen to the c's? Yeah. So I've got a plus c here, and then because of this minus here and this c here, they're going to actually cancel one another, and that happens every single time. So when we do definite integrals, we actually really just don't need to write the plus c at all. Okay, it's just not necessary because it cancels itself out. Okay, so I won't write them on anything in the future, but that's the reason why. All right, so we can do this with our calculator. We can do this by hand. These are not hard calculations. This particular one is not anyway. So if we want to take a calculator, let's actually grab it. I want to show you a couple calculator features today that are going to be helpful too. So might as well get that calculator out and do this for this one first. So go ahead. I'm going to show you two ways of doing this. I'd like for you to enter the general antiderivative without the plus c, of course, into y1. So that would be negative 3x squared over 2 plus 4x. Everybody good with that? We put in this right here. This is what I want for the moment into y1. We're going to change that in a second here. We're going to do something different, but this is what we're going to do first. We just want to evaluate at 5. We're going to evaluate at 2. There's 2 ways to do that in general. You could look at a table, and you could just put in 5 and get an answer out. And you can put in 2 and get an answer out, and these will be nice values. These are not bad values anyway because they're going to give you terminating decimal. So if your calculator is at decimal form, you're good to go. That's all great. Now, that doesn't always work, right? Sometimes you end up with things that are really ugly, and this is not a good process by which to do this. But for this one, we could do it. The other thing you could do is you could go into your regular screen, and we're going to run through a couple of steps that you've seen before. I want you to hit vars, go to yvars. Is everybody good? We find vars, yvars, and press enter. And then you press enter on y1. So right now on your screen, it should just say y1, and you can put in parentheses next to it 5. So on my screen right now, it says this. Right, that's what my screen says. And I'm going to put it all at once. I can. So minus y1 of 2. So I can do minus, and I can hit it again, vars, yvars, function y1 of 2, press enter. And the answer I'm getting is negative 19.5. If you turn it back into a fraction, you would hit math. Option number 1 is frac. And this would say negative 39 over 2. Either of those versions are perfectly acceptable. If this had said 19.6 repeating, we would not leave it like that. We're not going to leave a repeating decimal in our answer. We would turn it back into fraction form, and it would be a necessity at that point from the standpoint of accuracy. Okay, is everybody good? Okay, I want to show you another way to do this. Are you ready? Okay, I want you to go into y1. I want you to clear out what we had, and I want you to go backwards now. I don't want this to be y1. Hang on. I want you to put in this right here. Wow, that's not what I meant to do. Different class. I want you to put this in as y1 now, okay? So put your negative 3x plus 4 in as y1. Now, what I'm about to show you is going to give you the answer of negative 19.5 without ever finding the antiderivative directly. And that's fine. Your calculator can do that. I am still going to want you to show me an antiderivative and to show me that you're plugging in the 5s and the 2s. So everything that you see in these first 2 steps here, except for the plus c part, right? This you need to have, all right? We have to put those things down. You don't necessarily have to write y1 of 5 minus y1 of 2, but I want to see those 2 steps, right? That shows that you're actually applying the fundamental theorem of calculus, okay? But your calculator can find the answer directly for you as well. So I want you to go back into the regular screen. So second quit, you should be back in the screen where we found the negative 19.5 before. Everybody good? All right. I want you to hit math. And I want you to scroll down, and I want you to see that you've got a number 9. Math 9 should say FNINT. Does it say that? Okay. Select that. Now, depending on the calculator version that you have, what came up on your screen, I'll show you what came up on mine. Mine is an older calculator version. Mine actually says FNINT parentheses, okay? Some of yours actually put a script S, right? And they put a D over here, and then they have some little boxes going on. So it looks like this. There's like a little box right here, and there's a box here, and there's a box here, and there's a box here. Okay, everybody good? Does everybody's screen look like one of those 2 things? Okay, just out of curiosity, how many of yours look like the second one? Okay, and then how many look like the first? Okay, so it's a little bit split. All right, so just in order of the way I've done it, I'll go with this first one first. What we're going to put after this is we're going to tell it that we want it to be the equation y1. So those of you who have the version 1, walk through this with me. So I want you to hit vars, yvars, function, and pull up y1. And then on your calculator screen, there's a comma. You'll use that comma. The comma is underneath the sign button. And then you're telling it x. What you're literally telling your calculator is my function is in y1, and my variable is x. And then you're going to put a comma. And then you're going to put the lower limit of integration, which for us is a 2. And you're going to put a comma. And then the upper limit of integration, which for us is a 5, and you're going to put a 5. And you're going to press enter. Okay, did it tell you, for those of you who have that version, negative 19.5? Yes, wonderful. Okay, now everyone else who has the other version, it's going to match just like the function we started with. So you're going to put a 2 right here on the bottom. Maybe I should use the black. You're going to put a 2 right here on the bottom. You're going to put a 5 right here on the top. And you're going to tell it y1 here. You could type the whole thing in of y1 if you wanted, but we saved it in y1, so we're going to put y1 in here. Remember, you get y1 by doing vars, y vars, function y1, and then you put an x at the end. So you're just filling in all of that symbol form to match the original one that we started with. And when you press enter, it should also tell you negative 19.5. Does it? Yes. Okay. So that's option 2 for seeing how this works. You ready for option 3? Yes? You're all like, man, why do I need so many options? Well, options are good, and then you can pick which one you like later. Okay. I'd like for you to go into your calculator. It should still have the negative 3x plus 4. And I'd like for you to set your window to be a little bit bigger than 2 to 5. So I'm going to make my window go from 0 to 10. So I'm going to hit window, and I'll make my x minimum go 0, my x maximum 10. And I don't necessarily always know what my y min and max would be when I do that. And so the way that I can get the calculator to decide that for me is by going zoom fit, which is zoom 0. So right now on my calculator screen, it looks something like this. Yours looks something like that? Yes? Okay, excellent. Now I want you to hit the math button. So the calc button, excuse me. So you're going to hit second trace. So if you see the word trace on your calculator, right above it, it says the word calc. That's the calc menu. And do you see option number 7? Choose it. It will say on your screen, lower limit. That's 2. Press enter. Upper limit. That's 5. Press enter. What happened? What happened? It shaded it in, right? It shaded it in. So your picture should look now, shaded in, something like this. Does it look like that? Now, the value is on the bottom, negative 19.5, right? And this picture shows you why it's negative. The area, as we find it, according to the definitions of the things we've worked at, is supposed to be the amount of space above the x-axis. And this one's completely below, right? That's why it's giving you a negative. Not that the area is really negative, but it's showing you where the area is. And this one happens to be completely underneath the x-axis. Now there's some, give me just a second, Andrew. There's a couple things to be aware of on this one specifically. If this answer had been something that was a repeating decimal, like from your window, there's no way in this screen to turn it back into a fraction very nicely. There's also the fact that you actually really have to manipulate your window in order to make this work. If our window had not included from 2 to 5 and we told it to do this, it would have given us an error. Okay, so you have to be a little bit more careful on the setup to do this. Yes, Andrew, what's your question?
My calculator didn't do that.
You haven't typed anything yet. You have to do 2. Lower limit. Press 2. Hit 2 and enter.
Okay.
There you go. And then 5.
Okay.
Now it did it. Okay. Did anybody else not give them a screen that shaded it like this? Okay. Cool. Okay. You ready to try another one? All right. All right, this one is actually a fairly good example of a place where none of the techniques that we just used with the calculator are particularly friendly, in part because we're dealing with sign functions, but also in part because my limits of integration include an irrational number pi. So our calculator can give us an approximation just fine, but it will not be able to give us the exact answer, all right? So let's find the antiderivative first. That's what we're supposed to be doing. What is the antiderivative of 1? X, and the antiderivative of sine x? Right, negative cosine of x. Remember, we don't need the plus c. If you want to put it, you can, but there's no need. We do need that bar for our limits of integration, pi and 0. And then we're going to put the pi in for the x's. So I have pi minus cosine of pi And all of that is minus 0 minus cosine of 0. Okay, is everybody good? Yep, Kingston.
Do we have to put that bar there next to the exponential sign?
Yeah, so the idea is that each one of these lines is supposed to be equal to the one before. So if you left this off right here, it would be kind of like having a statement that says that these two pieces are equal, but they aren't because there's no limits of integration present on them. Does that make sense? So in order for each step to be equal to the one before, yes, they should be present there. All right, so pi is pi. I don't have to deal with that very much. What is cosine of pi?
0.
Is it?
-1.
Is it? Which one? We got two answers now. Do y'all know? And maybe it's neither of them. So we're right here. It's -1. Okay, so cosine values are x values. If it had said sine of pi, it would be 0. This one's cosine of pi, so this one is -1. So the negative's already here, and then I have a -1. And then I have, well, goodness, well, there's minus a 0. I don't know that I need to write that down. And then I have a negative here, so I think I'm going to have a plus now, right? I'm going to distribute the negative. What's the cosine of 0? Now I'm over here. That one's 1. So we end up with pi plus 2. Now, you can verify this, at least correct to an approximation with your calculator, right? You could put in the 1 plus sine x, and you could use that feature that we had done with Math 9, if you wish. But it won't give you pi plus 2. It'll tell you something like 8.28 ... It'll give you an approximation for it. So you could at least verify that the approximation matches, but you can't sort of drag back out of it that this value is pi plus 2. All right. There is a second part of this fundamental theorem of calculus. So the second fundamental theorem of calculus says the following. If f is continuous on AB and capital F of x is any one of these antiderivatives, a to x of f of t dt, then the derivative of the integral is equal to the original function. So back when we looked at these antiderivatives in section 4.1, we talked about this. We talked about the fact that doing an antiderivative is sort of the reverse of doing a derivative, right? It's an inverse operation. So it's the same thing that happens if you were to take a value and then you were to multiply by 5 and then you were later to divide it by 5. It would be unchanged from what it originally started at. That's what this is saying. Now, there are a little bit of fuzziness to this, right? I mean, we talked about in section 4.1, we have to do this plus c on there because it could be shifted up and down. So it's not exactly a perfect inverse match because we have this shifting that could go on. And you see something here where we've got t showing up, right? T is another variable. So that sort of feels like there's something else going on. And there is a little bit of something else going on here. And it happens when we have chain rules. So let me show you what happens with one that's really nice and clean. And then I'm going to show you what happens with one that's maybe not quite so nice and clean. Well, I said it that way, and it's not really quite true. Neither one's nice and clean, but they're nice and clean in different ways. They're not nice and clean in different ways. That didn't say very good. All right, let's look at 3. Notice on number 3. This doesn't quite look like what you saw in the previous problems. What about this is different than problems 1 and 2? Besides the fact that the directions are different, that's not what I'm talking about. There's a sine x as a limit of integration, right? It's not a number. I did not have 0 to 5, correct? Or 0 to pi or anything like that. I have sine of x, which is a function, and that's different. So if I were to take the derivative of this, I would end up having to take the derivative of something with sine of x in it. So I'm going to do this out the long way, and then I'm going to apply the fundamental theorem of calculus and show you how it's helpful to shortcut the system. Does that sound okay? So the directions here say they want us to find the derivative f prime of x. So what we're going to do first is we're going to find the antiderivative, because that's how f of x is defined, and then we will find the derivative. So here's what we're going to do. What is the antiderivative of t? No tricks, just what's the antiderivative of t? Thank you, t squared over 2. How about the antiderivative of 2? 2t. Yeah, it's 2t. We're doing t's for this one. Yeah, it would normally be 2x if we had x's. And our limit of integration from what we had seen before would be that this is sine of x and this is 0, right? Okay, so if we're doing this with all the tools that we have just built up in the first two problems, it would look like this. And then we would evaluate it. We say, okie dokie, I'm going to do sine squared. Actually, let me write that 2 as a 1/2 in front. 1/2 sine squared of t plus 2 sine of t. And then I'd have minus, and this one's not very exciting, it's 0 squared over 2 plus 2 times 0. So this whole thing is 0 at the end, right? So my original function that I was given is equivalent to having 1/2 sine squared t plus 2 sine of t. Now, that's not what I was asked to find, though. It wants me to find f prime. Okay, so now we're going to take the derivative of this. I realize you don't have much space to work if you've written this in notes, because we're going to do the shortcut, and it's a lot faster, a lot shorter. We're going to take the derivative. Well, what do we have to do when we have to take the derivative? Well, we first need to notice that sine squared makes it a chain rule, right? The chain rule part of this is what makes this a little tricky. Okay, so I've got a chain rule. That means I need to take the 2 that's the exponent of sine and bring it down to the 1/2. I rewrite the sine to the new power, which is a 1, like so. And then I would need to take the derivative of t, but the derivative of t, just like x, would just be 1. So this is a chain rule. It's not a super tricky chain rule, but we do need to be careful that we recognize that the 2 comes down, the sine power goes down by 1 to a power of 1. Oh, I'm sorry. I didn't say that right. I was looking at the t, and I meant to be looking at, come on, cut. There we go. We need the derivative of sine of t. I'm sorry. It's because I've got it written funny. That's why this is weird. I'm going to write it like that. Better. All right, what's the derivative of sine of t? That one's cosine of t. That's what I meant to do. So sorry. Okay, now we need the derivative of 2 sine t. So what is the derivative of 2 sine t?
2 cosine.
2 cosine of t. Sorry, thank you. Okay, and we would clean this up, at least a little bit. And this would now say that I have sine t, cosine t, plus 2 cosine of t. And I'd like for you to compare that back to the original piece that we were given, t plus 2 here. And if we put the sine of t in, or sine of x in, right? If we just flat out put sine of x in for t, it would look like this. Now, that's not quite what I have at the end. How is it different? If I compare this, which is just plugging in sine of t in for t, sine of x in for t, how is that different than what's going on in the very final step here? There's some cosines in it, right? Let's take the cosine out, like factor it out, but I'm going to factor it out behind it, just because it's listed second. Do you see the sine t plus 2 in there now? I don't know why I'm using t's. I meant to be using x's. I'm really struggling today, guys. I apologize. They're x's with everything that I'm working with. It's because I've done it on the entire problem, huh? I'm sorry, guys. They were supposed to be x's. Did I catch them all? I think so. All right. And I did up here too. Okay, let's try again. If I compare sine of x plus 2 to this piece down here, it's exactly what Joshua said. It's got that cosine of x that was not supposed to be there. Why did the cosine of x show up? Well, cosine of x showed up because it's the derivative of sine of x. So if you look back over here on this definition, it doesn't have a sine of x up there as an upper limit of integration, right? It just has x, correct? What's the derivative of x? 1. It doesn't affect anything, right? It doesn't change anything if I take the derivative of x. So when I work through this and I take the derivative of this antiderivative, if this is not x, like ours is on here, right? If it's not just x, we actually have to also include the derivative of x as a portion of what we're getting back here. So what you see is that the original f of x, this f is continuous. I get the same f right here, but it might have this extra little piece on the end. So let me show you how this is supposed to actually work here to make the process easier. Are you ready? I'm clearing my screen. Literally, here's what you have to do to use that theorem. You take what is here, and you write that you're going to do the derivative. We'll do it with x's like I'm supposed to this time. You replace the variable with this upper limit of integration. Sine of x plus 2. And if that upper limit of integration is not just x, you have to multiply it by the derivative of it. Derivative of sine of x is cosine of x. Which means all I had to really do was sine x, cosine x, plus 2 cosine of x. I don't take derivatives or antiderivatives with one exception. If the upper limit of integration is a function, I need the derivative of that piece. But the process is truncated, right? It's shortened. It's much simpler because of that property. Okay, that theorem helps us out a whole lot. So how is this one different than the previous one? I don't have a constant on the lower. Now I have a variable piece on each piece, right? Everybody seeing that okay? So what we're going to do is we're going to apply a property that we saw back in section 4.3. We didn't really see a great use for it. But do you remember there was a property that said, hey, we could go from the integral from a to b. If we wanted to, we could go from a to c, and then we could go from c to b. We could sort of break it into two pieces. Do you remember talking about that? We can break some interval apart. That's what we're going to do here. We're going to break this apart so that one of the pieces does have a constant, one of the limits of integration. So here's how this works. We're going to go from x, and you can use any constant you want. I'm just going to use 0. There's nothing special about 0. Use any number you wish, and it will work the same way. This is t squared plus 4 dt. And then plus, and then I'm going to go from 0 to 3 minus x. And t squared plus 4 dt. Now, that second one here looks a lot like this last piece, doesn't it? It's got a 0 at bottom. It has a function that's not, it's got x in it, but it's not just x as an upper limit of integration. It looks a lot like the one we just did. What's different about the first one, though?
It's on bottom.
Yeah, the x is on bottom. So we're going to use another theorem that we saw back in section 4.3 that says I can flip it upside down. I'm allowed to do that. I'm allowed to change this to look like this, but there is something else that gets introduced if I do so. Do you remember what it was? A negative. There needs to be a negative in front. So when I flip my limits of integration and I go from 0 to x instead of x to 0, I put a negative in front of this. I'm running into my equal sign. Let's shift it over a little bit. Okay. The other piece still stays the same. 0 to 3 minus x, t squared plus 4 dt. Okay, so the separating out of this makes this problem a little bit more challenging than the last one we did, but evaluating it is easier in terms of derivatives. In fact, that first one, 0 to x, looks exactly like what I have here. I got a constant on bottom, I have an x on top, and the derivative of x, right, is 1. So when I actually do this first piece, it's the most friendly we've seen. Has a negative out in front, but then the t just gets replaced by x. And because x's derivative is 1, I don't have to do anything if it bothers you to see that. Put a 1 here at the end to remind yourself. The derivative of x is 1. That's what we have for, this is f prime here now that I've done this. Okay, now that I've actually done the evaluation, I've changed it into f prime. The other half, however, when I do my evaluation, the t gets replaced by 3 minus x which will now be squared plus 4. But I do need to take the derivative of 3 minus x. It's not very complicated, but I need to do it. What's the derivative of 3 minus x? What is it? Not quite. 0 minus 1. So it would be a negative 1, right? Okay, so the derivative of the 3 is 0. The derivative of the negative x is negative 1. So we get a negative x, or a negative 1, introduced into it at that point. Now, we need to do some cleanup, but the cleanup that we still have to do is algebra, right? We're going to clean this up, simplify some things, combine some stuff if we can, and that sort of thing. But we've done the calculus part. We've applied the second fundamental theorem of calculus. So over here now, I'm going to distribute my negatives. This is negative x squared minus 4. Over here, I have a negative to distribute as well, but I've got to clean up that inside first. So I'm going to actually just leave it as it is and just clean up the inside first. So I have 3 times 3 is 9. And then, remember, you have to multiply this out, inner, outer, right? All that kind of stuff, foiling. So I'm going to have 9. And then I'm going to have, let's see, minus 6x plus x squared and plus 4. And then we'll combine those terms that are alike and distribute the negatives. So I have a 9 and a 4 would be 13, and I have a negative 13. I have a negative 6x, so I now have a positive 6x. And I have a negative x squared. So I have negative 2x squared, positive 6x minus 17. Does that look right? Okay, all good? All right. So we're going to use these ideas now to take a problem where it's written out in a little bit of language, right? We've got a little bit of verbiage around it, and we're going to find the area that it's describing. This wants us to find the area of the region bounded by y equal x squared, x equals 2, and the x-axis. So we're going to start out by drawing a picture. What does y equal x, I said it right, y equal x squared look like? That's a parabola. It looks like this, right? That was not good. Let's try again. That was better. There's my parabola. So this one's y equal x squared-ish anyway. What is the line x, or what does x equal 2 look like?
Just a line.
It's a line. What kind of a line? This one's vertical. X equals 2 is a vertical line. Okay, so we have x equal to 2. I'll change colors. It'll look something like this. So this is the line x equal to 2. And where's the x-axis? This is not a trick question. Where's the x-axis? Yeah, it's the horizontal axis. It's this one right here, right? This is the x-axis. So do you see the area trapped that it's describing? Yeah? Okay, so we have to get a, sort of a picture in our mind of what it's describing. It's this piece right here we're trying to find. So clearly my integral is an integral of x squared because it's beneath the x squared graph dx. But I do need to find my lower and my upper limits of integration because those were not given. The picture should find that for us. So I think the bottom one is pretty clear that it starts at the origin at 0. What is the x value it extends over to? 2, right? It's the vertical x value 2 that it gives us. So we're going to find this piece now. What is the antiderivative of x squared? X to the third over 3. Very good. We're going to evaluate it at 2 down to 0. So this is 2 cubed over 3 minus 0 cubed over 3. What's 2 cubed over 3? What's 2 cubed?
Just 8 over 3.
8. Yeah, it's 8 over 3, and 0 over 3 is 0, so this is just 8 over 3. Okay, so there's nothing difficult about the computation about this, but you do have to have the visualization to set it up properly, right? Yeah. Okay, the last thing in this section is actually going to do something called averaging. So we're going to find an average value for integrals. So if f is integrable on AB, then the average value of f on AB has that antiderivative piece that we've been working with, integral from a to b of f of x dx. But in the front, I've got a division factor or a multiplication by something, right? A 1 over b minus a. So I want to show you in picture form what this is doing, and I can do it with my last graph because we just drew it on the screen. So I'm going to flip back over there to show you. If you were to take this graph, what we're going to do is imagine the part that's shaded in red is a very thin piece of Play-Doh. Can you picture that? Can you picture like filling it in with Play-Doh there? And you're going to take that Play-Doh then, and you're not going to change the thickness, or it's going to mess it all up. I need it to be thin. Okay, so imagine the thin piece of Play-Doh doesn't change thickness. And you're going to change the shape, you're going to manipulate it, so that it's going to turn it into a rectangle. Okay, so let me show you what that would look like. It's going to be a rectangle with the same area that the red piece had. You're reconfiguring the space. Can you picture that? That's what averaging does. That's what averaging does to your grades, right? You lose all the specific values of your grades when we average your grades together, correct? That's what's happening here. You lose the shape of the curve, but there's some sort of piece of it that's coming out, and it's the averaging piece. And what am I really dividing by over here? Well, I'm really dividing by how wide this is. This piece at the bottom, right, if this one were being used, would go from 0 to 2. I'm dividing by the width of this rectangle. So what I'm actually finding is the other piece, which is the height. So the process by which we do this is not a challenging or difficult one. We're going to do this for one that we haven't seen yet before today. We've got the square root of x. We're finding the average value between 4 and 9. And we're going to look at a graph for this as well after we have done the calculation piece of it. So according to the formula we just found, the average value is going to be 1 over 9 minus 4, because that's the difference in the x values. The integral will go from 4 to 9. It is square root of x, but I'm going to write it more conveniently as x to the 1/2 dx. This is what the average value formula says I'm going to do, right? Okay. So I've got 1/5 in front, and I need the antiderivative of x to the 1/2. What's the antiderivative of x to the 1/2? X to 3/2, and then what? Over 3/2, or we can multiply by 2/3 if you wish, right? So divide by 3/2 or multiply by 2/3. And we're evaluating it from 9 to 4. Top is 9, bottom is 4. I'm going to clean a little bit up before I actually put the 9 and the 4 in. I'm going to write this as 2 over 15 in front. And I'm going to write this as the square root of x cubed at the back. Is everybody good with all of that in terms of rewriting? Okay, now we're going to put in our 9, so 2 over 15. And we're going to put in our 9, so it's the square root of 9 cubed. And then I'm actually going to put the 2 over 15 in front. We'll multiply that by it at the very end. And then I have the square root of 4 cubed. Now your calculator can do that for you pretty nicely. These are actually really nice values. I would encourage you not to actually cube before you square root. 9 and 4 are perfect squares, which means square rooting them will be nicer than turning it into a power of 3 and then square rooting, okay? What's the square root of 9? 3. And then 3 cubed is 27. What's the square root of 4? 2. And then 2 cubed is 8. Okay. Do you have to show all these pieces? No, you don't have to show all these pieces. This piece is the last piece I absolutely want to see. Everything after that, as we're simplifying, if your calculator wants to simplify it for you, would be okay. If we simplify this, multiply it out, and turn it back into, it needs to be in a fraction form because it will be a repeating decimal. It's 38 over 15. Okay, so I don't want to belabor the point that your calculator can do a 38 over 15. We're all good with 38 over 15? I want to show you what this has found for you, though. So I want you to take your calculator, clear out whatever we did before in there. And y equals, I want you to put the original function, which is the square root function here, or you can write it as x to the 1/2, either way. I'd like for us to take our window and really go from 4 to 9. So tell your window to start at 4 and to go to 9. And you can do zoom fit for the moment. It's not going to be where we're going to start our process of what we're doing. The shape actually almost looks linear if you look at this particular window. So in this window, my graph looks like this. It actually draws it dotted here, or it almost doesn't draw it at all, and dotted here, and you have a shape that looks something like this. Does yours look something like that? Yeah? Okay, that's not a great picture for the point. I mean, I can't see an x-axis or a y-axis. Those dotted lines that I drew in are not the x-axis and the y-axis. I'd like for you to adjust this just a little bit on your window. I'd like for you to click from window and make your y minimum 0, so we can at least see down to the x-axis. And if I shift that, now my graph looks like, hang on. I've still got this sort of a dotted imagery over here. And over here, I have this. And then my graph is now up here somewhere, kind of like this. Does it look like that now, ish? Okay. I'd like for you in Y2 to put the answer we got 38 over 15. So in Y2, I'd like for you to put 38 over 15 and just graph it. And when you do, the graph ends up looking like that. It's shifted up a little higher from that, from what I've drawn. So let me shift it a little bit. It looks kind of like that, doesn't it? So what did this do? Well, it balanced out these two pieces. Let me draw them in here. This area and this area match. Is that visually believable? Okay, that's what happened. Is it reconfigured where this piece was? So I know my width down here. My width goes from 4 to 9, right? So the width is 5. And this 38 over 15 is telling us what the height of the rectangle would be when we already had the area that we would have had. So the area itself would be the same underneath my curve, x squared, as it would be underneath that line, 38 over 15. It averaged it out. It balanced it. So I think there's some inside of WebAssign where they ask you to draw in this vertical piece or something like that, either to verify or to show something on the screen. I can't remember how it asks it, but this is what they're talking about. This value that you're finding with that 1/5 at the beginning, right, that 1 over 9 minus 4, is a balancing point for the area that would reconfigure it into the shape of a rectangle. And that's it for today.